Greetings, everyone. We have one last topic from Chapter 5 that we need to cover. It is a review topic from Pre-Cal. You did learn about trapezoid approximations there. So if you have notes on that from last year, you go check them out, and they're the same thing that we're going to be doing here. I may just put the notation a little bit differently, but that's always expected. So let's, for a moment, ask the question. Approximate the area bounded by the graph of f of x equals sine of x on the interval from 1 to 2. Now, of course, when we say approximate, if I don't give specific instructions in the question, then you could use left-hand endpoints, right-hand endpoints, midpoints, or even trapezoids. They all are Riemann sums that will give us an approximation. Of course, we're going to do trapezoid approximations here, but I'm not going to say that specifically yet, or I'm not going to write that down at the moment. So what we're approximating here is the definite integral from 1 to 2 of sine of x dx. Now, of course, we could just go ahead and compute it because by the evaluation theorem, we can find an antiderivative of sine of x, evaluate it at 2, evaluate it at 1, and then subtract and get the exact answer. But here we want to practice our approximations. And so let's take a look at some pictures of what's going on here. So this is the graph of the sine function between 0 and pi. And of course we're looking between 1 and 2. 1 is there, 2 is here. It's hard to read. Here's the approximation with just two trapezoids for a moment. And you can really see what the key is in doing this. We have, of course, to divide the region into two. So, of course, we take our interval and divide it by the number of trapezoids we're going to use. So we'll always have our delta x found in the same way as before, b minus a over 2, or in this case, 2 minus 1 over 2, which is going to be a half. So you can see 1.5 right here in the middle. And so we divide it up into those regions right here. And then the key to getting the trapezoids that we're going to be using to approximate the area is to then go to the points where these subintervals hit the curve. So I've highlighted the point on the curve at these endpoints for these subintervals. And then all we do is we draw a secant line between those points. Okay, so we draw the secant line like that. Now I've covered up a little bit because of the thickness of the pen that I'm using, but nonetheless, all we do is we connect those points like that, and then we have our trapezoids that are formed. Now keep in mind, a trapezoid has parallel sides, and one pair of parallel sides, and these are the parallel sides. So the trapezoids aren't in the usual orientation that you might be used to seeing them. Typically they're drawn with the parallel sides horizontal to you, and here they're vertical to you in these diagrams. So in order to do the trapezoid approximation here, we would of course need to figure out how to calculate, or remind ourselves how to calculate the area of a trapezoid. And I'll put that over here. The area of a trapezoid is, of course, b1 plus b2 times the height divided by 2, or the sum of the bases times the height divided by 2, or the average of the bases times the height divided by times the height, or just the sum of the bases times half the height. However you want to remember that. So in order to find the area that we're going to or approximate the area that we want to approximate, I need to figure out for each of these trapezoids, there's two of them here of course, I need to figure out the sum of their bases, so I need to figure out the length of their bases. The height, I hope is obvious, that's going to be our delta x. And so the area that we're trying to approximate here, well, the first base is going to be this left side here, and that's just the sine function evaluated at 1. And once we evaluate the sine function at 1, then we need to evaluate the sine function at 1.5, and once we do that, there's our two bases. And then the height, again, as we said, that's going to be delta x, that's 0.5, and then we'll have to divide that by 2. And then, once again, we're going to do that same process for this other trapezoid, so we're going to get sine of 1.5 plus sine of 2 all of that times 0.5, which I can't even fit because I wrote so carelessly here. Put that in over there, and then divide by 2. So all we're doing is we're just going to break up our interval into n subintervals using the same process we did for left-hand and right-hand endpoint approximations. And then we're going to connect each function value at the endpoints with secant lines. And once we connect with all those secant lines, we'll have our trapezoids, and we just find the area of each trapezoid, add them all up, and then there's our answer. Now this may look a little bit confusing here. Let me put the answer down. You can compute this on your calculator. You should get approximately 0.9364. Yeah. If you do this on your calculator correctly, and you should practice the skills that I showed in those earlier videos for using your calculator. It'll help you with the calculations. Now let's take a look at another picture here. Here's the same region but using 3 trapezoids, and here's the same region using 4 trapezoids. And as you can see, this is quickly becoming a very good approximation from just a few trapezoids. You don't need to have 50 or these to get a decent approximation in most cases, and so trapezoids tend to be pretty efficient in generating an approximation. So let's take a look at. I just want to set this up really quickly for this one. So, of course, delta x again is going to be 2 minus 1. This time over 4, since we have 4 trapezoids that we're going to use, and so each one has a width of 1/4. And so now I need to calculate all the bases. So for the first one, these are the 2 bases. Remember that I'd connect with a secant line over here, and that secant line would close off the trapezoid. So I need to figure out those 2 bases. But again, that's just evaluating our function, f of x equals sine of x, at 1, and then at 1.25, and then we have 1.5, 1.75, and 2. But I need to evaluate at 1 and 1.25, add those together, times the height divided by 2. So let's just generate this really quickly. So I'm going to have f of 1 plus f of 1.25 But then again, if I think about this, when I multiply that by the height, I'm going to multiply every single trapezoid by the same height, 1/4, and then divide by 2. So why don't I just factor those out and not have to worry about them anymore? So I'm going to have that divided by 2. I'm going to have the 1/4 over here. And so I don't have to, in fact, we'll put that as a 0.25 because it'll be easier for you to put in your calculator probably. So I don't have to write that 4 times in this example here. And then I'm going to use the height 1.25 again, because 1.25 that value's in the first and second trapezoid. Then I'm going to use 1.5, but then I got to use 1.5 again, and then f of 1.75. And then I got to use f of 1.75 again, and then f of 2. So notice that except for the endpoints 1 and 2, every other value gets used twice because they're in 2 different trapezoids. The 1.0 is only in one trapezoid, and the 2.0 is also only in one trapezoid. And so we only need to do that one time. Those each one time, but every other one needs to be done twice, part of 2 trapezoids. If you do this, let me get an approximation for us from my computer. Using 4, you should get 0.9155. I'm sorry, 0.9515. 0.9515. The 5 at the end there is a 4 that gets rounded from the next digit that's a 6. You can actually just truncate if you want and leave it as a 4, but there's your approximation. So again, with trapezoids, it's just another Riemann sum, and they usually do a pretty good job, and you just need to go practice, okay? So we'll do one more together, and then you'll have to practice the rest on your own. Okay, so approximate the area bounded by f of x equals the square root of the quantity x minus 1 plus 2 on the interval 1, 3 using 3 trapezoids. And just to give you a picture here, this is a picture of the area that we're trying to approximate. I actually have about 25 trapezoids on there, so you can actually see a dash of white right over in there between the curve and the blue. But we're not going to use 25 trapezoids. We're going to use 3 trapezoids, and so it won't look quite like this. But the function, the square root function that we have, is a fairly straightforward square root function, shifted 1 unit to the right and up 2. And so what we're approximating here is the area bounded by, or the definite interval from 1 to 3 of the square root of the quantity x minus 1 plus 2 dx. This is the area we're trying to approximate. So go ahead, pause, go work this out, come back and get an answer, and we'll compare. Alright, I left the actual area under the curve, well, of course, to that many decimal places, on the screen for this with the 3 trapezoids pictured, because I just wanted you to see what you were aiming for. We'll get the approximate area up there in just a moment. You can, using the substitution method, figure that exact area out, figure out what the antiderivative is. So if you want an extra challenge, go back and evaluate the definite integral right here using a u substitution, and see if you can get this answer here. But nonetheless, our delta x is going to be, we're looking on the interval from 3 to 1, so it's going to be 3 minus 1, and we have 3 trapezoids, so it becomes delta x is 2/3. And so our endpoints of our subintervals are going to be, I accidentally hit the button to move to the other screen. So x sub 0, of course, is going to be 1. X sub 1 is going to be 1 plus 2/3, which is 5/3 as an improper fraction. X sub 2 is going to be 5/3 plus 2/3, which is going to be 7/3. And then x sub 3 is going to be 7/3 plus 2/3, which is 9/3, but 9/3 is just 3. So these are all the endpoints that I'm going to be using to calculate the bases for each trapezoid. So the area that we're approximating here is going to be found by, remember, as I said before, we can factor out the delta x, which is 2/3, and then we can factor out the dividing by 2, which I'm going to put as times a half here. And now all we have to do is sum the function at the proper values, the bases, over and over again. So I need f of 1, then I need f of 5/3 for the first trapezoid as one of its bases, and I need f of 5/3 for the second trapezoid as well. And then I need f of 7/3 for the second trapezoid, and f of 7/3 for the third trapezoid, and then I need plus f of 3 for the last trapezoid. So just to highlight what's going on here, these two are the bases for the first trapezoid, and then these two here are the bases for the second trapezoid. And then, I hope this doesn't get overly confusing here, but these two are for, wow, I messed that up. I'm trying to pay attention to my color more than what I'm supposed to be doing here of overlapping. These two are for the second, and then these two are for the third. But you see we're using some of these twice, okay? The middle ones we use twice. Now if you run that through your calculator, and get the approximation. It is about 5.7855. And there you go. Hopefully you got that answer. Go study.